Hi, my name is Shiting Xiao, and this summer I'm working with Dr. Maxim Likhachev and his team in the search-based planning lab. For my project, I am working on a novel GPU-based algorithm for six-stop object pose estimation. For robots operating in real-world environments to interact with objects in a safe and reliable manner, they need to be able to accurately estimate objects' location and orientation. Tasks like manipulation require the perception algorithm to identify objects of varying shape and texture in real time and in different environments such as occlusions, clutters, changing lighting conditions, and so on, which makes it a challenging problem. The success of convolutional neural networks on 2D object detection has inspired a family of data-driven techniques that use deep neural networks for pose estimation from RGBD inputs such as pose and dense fusion. These discriminative methods predict the pose from the given observed scene through regression, key point localization, or classification. An alternative is to use deliberative approaches that rely on rendering, synthesis, and cost estimates to find the best explanation for the observed scene. Discriminative methods are very fast. However, these methods require a large set of training data and extensive annotation of ground truth poses. Deliberative approaches don't need large dataset, but they tend to be slow. Specifically, PERCH is a recent work that introduces a global matching objective function and does a search in a globally efficient manner of a tree structure. It guarantees high accuracy but is slow due to limited computational power. In the recent work PERCH 2.0, the algorithm improved the original framework by rendering thousands of candidate poses in parallel on the GPU using RGBD data and searching for a global optimum like PERCH. This figure shows the six-stop pose estimation pipeline of PERCH 2.0. The input image is passed through a standard instance segmentation network, obtaining object labels and segmentation masks. Then we generate six-stop pose proposals for the detected objects through parallel rendering of each pose proposal on GPU. With the help of GPU acceleration, the search runtime can be reduced by an order of magnitude. However, prior to this work, the algorithm uses uniform sampling to generate pose candidates. It samples equidistant viewpoints from the unisphere and throws all of the viewpoints into the rendering pipeline to calculate the cost of the poses, which could be inefficient due to the lack of use of the geometric information of the objects. The predictions flow from the discriminative side to the deliberative side, but there is no feedback of information. Therefore, in this work, we aim to incorporate a neural network for learning the geometric features of the objects based on the cost calculated by PERCH 2.0, and to use that information as feedback to speed up the pose sampling. The cost here measures the differences in RGBD information between the rendered scene and the observed scene. We formalize the problem of learning as a task to learn a function G that predicts a score for each rotation viewpoint R based on the mask input image I and the mask point cloud P. Specifically, we're following a dense fusion-like network to extract pixel-wise color feature and geometric embedding to estimate the score of each viewpoint. The mask input image will be passed to a convolutional network that maps each pixel in the image crop to color features. The masked 3D point cloud will be passed to a point net-based network that generates geometric features. Then a pixel-wise fusion network combines both embeddings and outputs the estimation of the scores of each rotation viewpoints. For the training, we are using YCB video dataset. The ground truth annotation contains scores of n-sampled viewpoints for every input image that have been calculated based on PERCH 2.0 run costs. We use binary cross entropy loss combined with a sigmoid layer as loss function to measure the model error. The figure shows the comparison between the predictions made by PERCH 2.0 and the network. The top row shows input images and the top three most likely poses predicted by PERCH 2.0. Bottom row shows the top 3 most likely poses predicted by the dense fusion network. We calculate the cosine similarity between the predicted scores and the ground truth scores and get the average similarity around 73%. We also perform experiment to answer the following question. So if we want to keep the most likely poses predicted by PERCH, how trustworthy is our pose sampler? The table shows the mean accuracy for the top K poses classification. From the table, we can see when we prune half of the samples based on the predicted scores, around 80% of the most likely ground truth poses are preserved by the pose sampler. To conclude, we propose a continually improving self-supervised pose sampler that enables the speed up for the current deliberative framework. For the future work, we plan to apply color-based augmentations to increase the amount of the training data and improve domain robustness. We also plan to conduct more experiments to demonstrate the trade-off between accuracy and runtime speedup when incorporating the pose sampler in PERCH 2.0 workflow. Thanks for watching.